Hi, I'm Daniel Kane. I'll be talking about SQ lower bounds for learning half spaces with Massart noise. This is joint work with.
We're not ready.
Okay. Okay, sorry.
Yeah, sorry.
Daniel, I'll tell you a secret. You can take a few more minutes because there's a break afterwards. So
Okay, great. So now we're ready. So we'll have Daniel Kane presenting SQ lower bounds for Massart noise.
Yeah. Hi, I'm Daniel Kane. This is joint work with Ilias Diakonikoulos, who was just speaking. He talked about this general non-Gaussian component analysis problem in SQ lower bounds and said there were a bunch of applications to more specific problems. And this is sort of an overview of the kinds of work that you have to do to adapt this framework to get lower bounds for your problem. The basic topic of this is learning half spaces. So for this, we define a linear threshold function, or an LTF. This is a Boolean function on R to the D given by f of x is sine of v dot x minus t. So you take x, you evaluate this linear function, and you determine whether it's positive or negative. And the basic problem that we're going to be looking for is that of learning linear threshold functions. So there's some unknown distribution d on R to d and some unknown linear threshold function f. You're given samples x, y, where x comes from the distribution d and y is equal to f of x. And you'd like to learn a hypothesis h such that the probability that h of x is not equal to f of x is, say, less than epsilon. And when you put it this way, this is actually reasonably well known. It's been known for some time that you can solve this problem in something like polynomial in d over epsilon, time and samples. And these results are pretty well established these days. But things become a little bit more complicated when you talk about noise. And it's somewhat unrealistic to assume that your data is 100% accurate. I mean, maybe there's some small amount of model misspecification where like the correct model to be looking at isn't quite a linear threshold function. It's, a little bit off. Or there might just be some kind of errors that show up where some small fraction of the time there's noise in your data and you don't get the correct x or value or the correct y value. And there's some small probability that y is not equal to f of x. And the question is, what kinds of learning are still possible under these kinds of assumptions? And before we get into any details of this, we first need to ask the question, what noise model should we be considering here? And so there are a few to look at. Maybe the most natural is that of agnostic noise, where you allow for basically arbitrary but uncommon errors. Now, you need to be a little bit careful about how you define this question, because you can no longer hope to perfectly recover the function f, because an adversary adding errors could just add errors so that instead of seeing y equal to f of x, you see y equal to f prime of x, where f prime is some nearby threshold. And so generally the way that this gets phrased is you let d be some distribution on R to the d cross plus minus 1. And you let opt be the probability that f of x is not equal to y. So this is basically the smallest error that you can achieve with any linear threshold function. And now, given these samples x, y from d, you want to learn a hypothesis h such that the probability h of x is not equal to y is less than opt plus epsilon. And the merits of defining it this way is that given that you don't need to do better than opt, this is at least information theoretically possible. And in practice, opt plus epsilon is often too much to ask for. So sometimes we'll settle for, O of opt plus epsilon or even poly opt plus epsilon. But generally, we want something that, the error goes to 0 reasonably quickly as opt goes to 0. And unfortunately, for linear threshold functions, this might be too much to ask. So there's a result by Daniele from about 5 years ago that says, under some plausible hardness assumptions about random KXOR problems, there is no polynomial time algorithm that distinguishes between, on the one hand, the case where opt is exponentially small and say log d to the 0.99, And on the other hand, the case where opt is only slightly less than a half. And on the one hand, this means that it's actually impossible in polynomial time under these assumptions to get error much better than a half, even if opt is this small, almost polynomially small in the dimension D. I'll also say that this result, you can pretty easily use its techniques to get SQ lower bounds with very similar looking parameters. And what this says to us is that if we really care only about polynomial time algorithms, that the agnostic noise model is perhaps too hard. We can't really expect to get very much out of it. So we'd like to look at an easier noise model. And maybe the easiest noise model to look at is random noise. So if we have a sample with random classification noise at a rate eta, what this means is that we sample x according to D, and then we set y equal to f of x with probability 1 minus eta and minus f of x with probability eta. And so basically each point we are randomly and independently flipping the value of y with probability eta. And fortunately, random classification noise you can also deal with. So it's been known for some time that even with random classification noise, you can learn the linear threshold function to error eta plus epsilon in, again, polynomial samples in time. And eta plus epsilon maybe doesn't sound so good until you notice that that is the same as opt plus epsilon in this case, because every sample gets corrupted with probability eta. There's no hope of getting an empirical error less than eta just because that's the noise rate. And it's a little bit instructive to look at the proof. And one way of proving this is that random classification noise behaves very well with respect to statistical query algorithms. In particular, if you've got some test function g, what is the expectation of g of xy, where y comes with this random classification noise? Well, there's a 1 minus eta probability that y is equal to f of x, and then you just get these sort of expectation of g of xy with no noise. And there's an eta probability that you flipped y and you get the expectation of g of x comma minus y with no noise. Now, if you sort of combine these together, I mean, what you get basically is that, well, if you given any function h, we can try and find a function g such that these two equations hold for all x. And then this you can solve for g just using linear algebra. And then if you plug this into the above formula, you'll note that the expectation of g of xy with random classification noise is the same as the expectation of h of xy without any noise. And the point is that by sort of making the noise cancel out, you can simulate noiseless statistical queries, even with random classification noise in the samples that you see. And in particular, since there are statistical query algorithms for learning half spaces, you just use those, you use this to reduce to the statistical query algorithms, and then you're done. And to me, this algorithm suggests that random classification noise is actually not a very good model. It's somehow too predictable. There are good algorithms in the model, but they depend on being able to make the noise exactly cancel out in these expectations. And my intuition says that in most real world situations, those algorithms will not work because the noise is not going to be so predictable that you can get it to cancel out in this way. For example, we might expect that in real world problems, some examples, say maybe examples very far from the decision boundary, will almost never be misclassified, whereas examples very close to the decision boundary might be misclassified with much higher probability. Now, it might not sound like having some examples having a lower probability of misclassification will make things harder, but it would actually mess up these particular algorithms that we're using. And so this suggests, at least to me, that we need a better noise model than random classification noise if we want to understand real problems. So a step up from this is what's known as Massart noise. So a sample with Massart noise at some rate eta, what you do is you sample x from your distribution D as always, And then there's some function eta of x that's pointwise bounded by eta. And you let y equal f of x with probability 1 minus eta of x and minus f of x with probability eta of x. So this is almost the same as the definition of random classification noise, except that the noise rate is allowed to depend on x. The samples, they still have independent probabilities of being flipped, but the probability of flipping the value of y is allowed to depend on the value of x, as long as it's still pointwise bounded by this number a. And it was an open question for a while whether you could learn with respect to this Massart noise. And a couple of years ago, Ilias and a couple of his other co-authors resolved this, that you can learn a linear threshold function with Massart noise to error eta plus epsilon in poly d over epsilon samples in time, which is great. Now, this result looks very similar to the result that we had for random classification noise, and so we might think that we're done, but we're not. Because for random classification noise, opt is equal to eta. Like you've got eta noise everywhere, and so you cannot expect to learn to error better than eta plus epsilon. And in fact, if you learn to error eta plus epsilon, that means you've actually learned the sort of noiseless function to error something like epsilon. However, for Massart noise, the optimal error might be much, much smaller than eta. Eta is now just a pointwise upper bound on our error rates. It might be the case that with high probability over x, there is no noise on y, and maybe only with very, very tiny probabilities does the noise rate approach anything close to eta. And so the real question now is, can we do better? Can we learn maybe to error opt plus epsilon? Now, that has been known for not very long, but for a little while to be impossible. There's a recent result that says there's no SQ algorithm with polynomial accuracy in queries that can learn a linear threshold function with Massart noise to error opt plus little o of 1 for all values of opt and eta. Now, this says opt plus epsilon isn't possible, but it's still not great. It doesn't answer, maybe we could learn error o of opt or poly opt, or maybe this can work for certain values of opt and eta or something like that. And the general question that we'd like to answer is, when you're learning half spaces with Massart noise, what is the best error rate that can be obtained, that you can learn to efficiently, as a function of both opt and eta? So I give you some problem. I promise you that opt and eta are going to be these particular values. What is the best error that you can hope to learn to efficiently? And unfortunately, the main result here is that the situation is still not great. So the theorem that we prove is that there's no polynomial query and accuracy statistical query algorithm that learns a linear threshold function with Massart noise at rate, say, eta equals a third, so constant error rate, to error better than 1 in poly log of the dimension, even when you are guaranteed that opt is exponentially small in log d to the 0.99. So things to note. Firstly, the opt here that we have is comparable to Daniele's result, which was in the much, much sort of worse agnostic noise model. However, the achievable error that we have is worse. Even in these hard examples, it is possible to learn to error 1 in poly log d. Now, we know from the upper bounds that there will always be, we can't do as well as Daniele's result, where you can't learn to error much better than a half, because it is possible to learn to error eta plus epsilon. But it would be nice if the actual bound that we had was closer to that. Okay, so that's the result that we're going to try and prove. And so the rest of this talk is going to be sort of about how do we prove that. And for this, we should recall from Ilias's talk, how do you prove SQ lower bound? So there's this non-Gaussian component analysis problem. If you have a distribution A that matches K moments, and he used M, I'm using K, slight difference, with a standard Gaussian, then an SQ algorithm that distinguishes between the standard Gaussian and this sort of thing that's A in the V direction and Gaussian in the orthogonal directions either makes queries of very good accuracy or makes an exponential number of queries. Now, for our purposes, we're going to need to be able to deal with distributions that don't quite exactly match moments with the standard Gaussian, but using basically the same techniques, you can show that if we only match moments up to some error nu, we get the same lower bounds, except tau increases by something like nu squared. Now, the non-Gaussian component analysis technique is great for showing that it's hard to learn distributions. But our algorithm, we're trying to learn functions. Our algorithm sees this distribution over pairs x, y, but y is Bernoulli. Y is a plus minus one random variable. There's no way we're going to be able to fool a statistical query algorithm into thinking that y is maybe Gaussian distributed when it's really plus minus one. And so instead of tricking the algorithm to thinking that the whole distribution over x, y is Gaussian, what we're going to try and do is we're going to try and fool it into making it hard to distinguish between the conditional distributions, x conditioned on y equals 1 and x conditioned on y equals minus 1. We want both of those to be hard to distinguish from Gaussian. And it turns out that that's enough in general. So the new lower bound is somewhat more complicated. We have two distributions, A and B on R. They match k moments with the standard Gaussian to error nu. For this new distribution, we have a probability P and a unit vector V. We're going to let PV be the distribution on R to the D cross plus minus 1, where with probability P, y is equal to 1, and x is this PAV distribution. And with probability 1 minus py is equal to minus 1, and x is this PBV distribution. So here, if you like fix y, you've got one of these hidden direction distributions that are hard to distinguish. And the claim is that any SQ algorithm distinguishes this from a standard Gaussian cross an independent y value, where plus and minus 1 come with these same probabilities, p and 1 minus p. Again, it either makes queries of very good accuracy or makes an exponential number of queries. So this is a lower bound. If we want to prove an SQ lower bound against learning an LTF with Massart noise, all we need to do is construct an example of this form where P sub v is an LTF with Massart noise. How hard can that be? Well, unfortunately, that doesn't actually work, because you can show that any distribution A, which even approximately matches, say, 1 in epsilon squared moments with a Gaussian, has the probability that A is bigger than a threshold T is equal to the probability that G, the Gaussian, is bigger than T plus O of epsilon. And we actually can't afford for this to happen for both the conditional distribution of x on y equals 1 and the conditional distribution of x on y equals minus 1. If you look at the threshold, then one of the two of those at least needs to be almost certainly less than t or almost certainly bigger than t when the Gaussian isn't. And so to solve this problem, we're going to need to find another way of phrasing. We're going to need to produce this sort of non-Gaussian component analysis problem that isn't itself an LTF, but corresponds to a linear threshold function in some more complicated space. And the way we're going to do that is by looking at polynomial threshold functions. So a degree k polynomial threshold function, or PTF, is a function of the form f of x is sine of p of x, where p is some polynomial of degree at most k. And the thing to note is that a polynomial threshold function is just a linear threshold function in the monomials of x. More specifically, if we define v sub k of x to be the set of degree k monomials of x in Rn, then f of x is equal to g of v sub k of x for some linear threshold function g. And so in particular, if we have some x where some f where it's really hard to learn f, then equivalently there's this linear threshold function g where it's really hard to learn g. So in particular, we need to show that there's that you cannot learn a degree k polynomial threshold function in poly n, polynomial in the dimension of this bigger space, polynomial in d to the k samples and accuracy. Because then this will give you this higher dimensional LTFG that you can't learn in polynomial samples and accuracy in the dimension on which g is defined. Okay, so how does this work now? So what does this distribution need? Well, this construction needs two distributions, A and B, for our sort of conditionals on y equals 1 and y equals -1. We also need a degree k PTF. And a degree k PTF in one variable is basically just a union of k over 2 intervals. So we need A and B and J, which is a union of k over 2 intervals. And they have to satisfy a bunch of conditions. A and B need to approximately match many moments with the standard Gaussian. In fact, they need to match more than k moments because we need lower bounds to be better than d to the k. Furthermore, we want opt to be small. So all but opt of the mass of B should be supported on J, and all but opt of the mass of A should be supported on J complement. Finally, we need this pair A and B to be given by this appropriate polynomial threshold function with Massart noise. And that means that once we condition on line in J, the output should be, with probability at least 2/3 should give us y equals -1. And when we're on J complement with probability at least 2/3, we should get y equals 1. And what this sort of boils down to is it says that B should be at least 2A on J, and A should be at least 2B on J complement. And there's a little bit of subtlety here because we can really adjust this parameter P, sort of this a priori probability of seeing +1 or -1 in the output of our function. And basically what this means for this is that A and B don't have to be distributions with the same normalization. One of them can be an unnormalized probability distribution with total mass more than 1. Okay, so we need to find A, B, and J with these properties. How the heck do we do this? And the basic construction comes from this idea that we're going to let B be a net of Gaussians. So it's a mixture of Gaussians. They've got with epsilon and separation delta. The overall envelope they satisfy is some bigger Gaussian. And it's not hard to show that this matches, in fact, many, many moments with the standard Gaussian to error approximately e to the -1 in delta squared. Now, what's J going to be? J is going to be a union of k over 2 intervals around sort of small intervals around the peaks of the k over 2 closest to the origin of these Gaussians. And it's not hard to build this and show that all but something like e to the minus delta k squared of the mass of B is in J. Okay, so that's B. What's A? We're going to start with A being just a taller Gaussian, sort of this unnormalized thing. This matches moments exactly with a Gaussian, which is great. And it is bigger than B on J complement because we made it bigger. The problem is that we need to fix this so that A is smaller than B on J. And to do this, we've got a trick. We're going to sort of move the mass of A that is on J off of it. And we're going to do this in a way without changing any of the first M moments. And the lemma here is that if you have a distribution D on some interval, and you have a sort of sufficiently small subinterval in the middle of it, there's a new distribution that's supported on the original interval minus the subinterval that matches M moments with the original distribution. And the proof here is, it's not terribly complicated. Basically what you do is you remove that little bit of probability mass, and then you just have to modify the probability density function so that you match these M moments again. And well, basically you need to have an M+1 parameter way in which you can modify the probability density. And for that, and then once you have that, you just sort of do some linear algebra to make the moments match again. And there are a bunch of details to get the right parameters here, but the basic idea is relatively simple. Once we have that, we can just apply this modification to A around each interval of J. So each interval of J is a tiny interval. We can modify A on some bigger interval so that we move the mass off of J, but keep the moments the same. So we have some distribution here. Now A has no mass on J, which is great. And so just looking at the parameters here, and this is the dimension of the underlying LTF. This is d to the k. So k is approximately log n. We need that that exponential of 1 in delta squared, this is the error to which we match moments, is bigger than the complexity. It has to be much bigger than n. So delta is going to be smaller than about k to the minus a half. And the opt that we get is like e to the minus k delta squared, which is about e to the minus k, which is almost inverse polynomial in n. And finally, epsilon, this interval width that we get. This is like, it has to be less than 1 in m squared for this moment matching thing to work. And that means it has to be less than about 1 in k squared. And this is a bit of a problem because we need a to be taller than b off of j. And this means that the normalizations of a and b need to differ by something like delta over epsilon. And that means that this probability p that like talks about the probability of getting 1 versus minus 1 sort of a priori in our distribution, it's going to be very unbalanced. It's going to be unbalanced by like epsilon over delta, which is like 1 in poly log n. And that means that even though it's hard to distinguish this family of distributions from something where x is independent of y, the y's that you're seeing are heavily unbalanced. You can just return a constant hypothesis y and only have error about 1 in poly log. Now, doing any better than that will break this thing. Doing any better than that will force you to distinguish between being a distribution from this family and being something where x is independent of y, and that therefore is SQ hard, so you can't learn to error better than 1 in poly log of the dimension, but you can do that efficiently. Now, there is a more recent refinement of this technique that shows that it's hard to get better than constant error, even with very small values of opt. That sort of uses some of the same tools put together a little bit differently. Basically, the constructions with A and B is now slightly more efficient. But yeah, so in conclusion, you can learn linear threshold functions with Massart noise to error eta plus epsilon, but you cannot hope to do much better than that, even if you are guaranteed that the optimum is quite small. And more generally, hopefully this is given sort of a feel that the SQ lower bounds are a useful tool for getting evidence of hardness for function learning problems. Now, for this particular area, further work, I mean, it'd be nice on the one hand to get similar results via reductions from some sort of standard hard problem rather than results in this restricted model of computation. It would also be nice to sort of extend these kinds of techniques to get lower bounds for learning other linear models like ReLUs. And there's some difficulty doing some of that with statistical query lower bounds because basically the kinds of SQ dimension arguments that we are using tend to only really work when the distribution that you're working with has full support. And here we were able to get away with it because, I mean, y was plus minus 1 valued. We have basically full support. It's fine. But when you start looking at real valued functions, they tend to be supported on some measure 0 set, and it's very hard to get SQ lower bounds to work in that context. In any case, I'm probably a little bit over time, but that's all I had to say. Are there any questions?
I guess one question is like for the Sibikov noise model, do you hope to get even stronger hardness results, or this one's already quite strong? Like,
I mean, so the constant error here, I mean, already shows that you can't learn to better than constant error, even if yada, 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 with Sudakov noise. I mean,
Sudakov. Sudakov is someone else. It's Sudakov.
Oh yeah, so I mean, it should already give some sort of result there, since Subakov is some subset of Massart. I'm not entirely sure what kind of bounds you would want that are better than that. I mean, for any parameters of Subakov noise, you can probably learn Well, okay, fine. You might hope to show that you can't learn to error better than a half, even with relatively weak Subakov parameters. But I guess we haven't looked into that.
Can I ask a clarification question? Can you hear me? Daniel, can you hear me?
Yeah.
So can you go back to the slide with the assignment and can you make it a little bit more complicated? What do you mean by constant there?
Here,
Yes. When you say constant, can you make it a little bit more precise?
I mean, well, I mean a constant. You can get a little bit more precise, which says that for any for this constant, I mean, so this constant holds when eta equals a third. In general, you can show omega of eta.
Okay, that's what I wanted to do. Okay.
Yeah, let's go on break until 11:10, and yeah, so I'm good.